For the determination of the concentration of chloride using ion selective electrode experiment, you're going to be using a chloride selective electrode to determine the chloride ion concentration in a couple of water samples. The first thing you're going to do in order to perform this experiment is compare direct calibration and standard additions. These are two different methods of making a calibration curve. Direct calibration you've done before. This is where you have measure a response. You put that on your y-axis for some concentration. Standard addition is a little bit different. The standard addition calibration curve is slightly more complicated than what you see with a typical direct calibration curve. You're still measuring some sort of response and something related to concentration of your unknown or related to concentration of the analyte goes on your x-axis. We're going to get into all the details of this, but here what is interesting is that the x-intercept gives you the concentration with some algebra involved of your unknown. Typically with direct calibration you make a series of standards and you measure each of those concentrations. With standard additions it's slightly different. There's a couple of ways to do it. You can make a series of standards that contain unknown plus some very concentrated solution of analyte and then measure those. That's called, and they all have the same volume. That's called constant volume. But you can also do varying volume standard additions where you take some beaker and you put in your unknown, so the thing you want to measure the concentration of, and then you add in spikes of standard with your analyte with the high concentration, and you measure that. Then you add in another spike and then another spike, and you measure each time. This is what we're going to be doing in this experiment, and I'm going to go into a little bit more details here, a few more details. So we're going to compare direct calibration and standard addition, and what you're going to do first is measure the chloride concentration in what we're calling synthetic tap water. All synthetic tap water is some water where I've added some known amount of ions. So we know the chloride ion concentration. It's going to contain other ions as well that are very commonly found in tap water at the same concentrations approximately as found in tap water. The reason why we're doing this is because if we know what concentration of chloride to expect, we can determine which type of calibration is more appropriate for determining chloride concentration using ISEs in tap water. Or water that contains a matrix. So matrix is the things other than the analyte, other than the chloride in this case, that we're measuring. So once we've determined which method is best, you're going to measure the chloride concentration in two unknown samples, or two real samples. And you are providing these. So if you haven't collected a water sample, now's a great time to do it. People like to bring in tap water from the places where they live, or bring in natural water samples. Any of those things are fine. Okay, so how are we going to make solutions? First things first, all the solutions need to contain 2% ISA. Okay, the acronyms get a tiny bit confusing in this experiment. ISA is ionic strength adjuster, and so this makes sure that the ionic strength of all of the solutions are going to be approximately the same, so that the ionic strength of the solution is not affecting the readout of our ion selective electrode. Okay, so all the solutions have to contain 2% ISA. And the other thing that's important to note is that all concentrations need to be reported in parts per million. Okay? If we're not in parts per million, we're not going to grade your results. And if you don't grade your results, that means you get a 0 on that section for the lab reports. The chloride concentrations in the synthetic tap water are going to be reported in parts per million. When you make your standards, you should make everything in parts per million of chloride. Okay? So I'll take all of that into consideration. So your standards for direct calibration need to be prepared in volumetric flasks, and the easiest way to do this is with serial dilution. In serial dilution, you're going to make a concentration of chloride ion in one of the flasks. You're going to take some of that solution, put it into another flask, and dilute. Take some of this solution, this new solution, put it into the next flask, and dilute. So making these a serial of concentrations, each one less concentrated than the one before it, obviously. So again, I said that everything needs to contain 2% ISA. So in order to prepare this first solution, make sure that it contains 2% ISA, and we're going to say U is the unknown. When you take some quantity from this first flask, make it easy on yourself so that when you go to make this 2% ISA and some amount of unknown, you don't have to add a weird volume of ISA. So you want to be able to add, say, 1 milliliter of ISA or 2 milliliters of ISA or whatever it is, some easy number or some pipette that you have to make sure that this solution is also 2% ISA. If you don't add ISA to the solution, it's no longer 2%. You're only based the ISA percentage is only based on what was in the first flask. So you need to make sure that that each serial dilution contains 2% ISA. For the standard additions, okay, you're going to have your beaker, and it's going to contain unknown. So again, that's U. But it also needs to contain 2% ISA as well. So keep track of volumes here. This is incredibly important for the standard additions. Okay. So you've got your first your beaker with your unknown and some amount of ISA to make it 2%, and then you're going to measure. You're going to measure the response on the ion selective electrode and write this down. Okay. Then you're going to add to this same beaker, so it already has the unknown and 2% ISA, you're going to add some spike. This is going to contain a concentrated amount of chloride ion. And you're going to want to add a small volume of this. So that's why we make it extra concentrated. But this also has to contain 2% ISA, ISA, in order to keep our ionic strength the same for each of these solutions. So you add this spike, you measure the response on the ion selective electrode. Then you're going to add another spike, and you're going to measure the response on the ion selective electrode, and again and again. So from these two things, you're going to be able to do two different calibration curves, okay? Your direct calibration and your standard addition. You're going to compare these, as I mentioned before. So let's look at the math that's underlying our calibration curves. So first, let's look at the direct calibration. This is based on the Nernst equation, which I have shown here, where we have our potential, okay, measured in volts, is proportional to the concentration of the chloride ion. Okay, so that's our X value in this case. X could be any ion. And you'll notice we have K, which is dependent on the electrode, and beta, which is also dependent on the electrode. If beta is equal to 1, then the response of the electrode is Nernstian. You can actually determine based on your direct calibration curve if your response is Nernstian. So if you look at this equation, it's actually in the form of y equals mx plus b. Okay? Where log of the concentration of chloride ion is going to go on our x-axis of our calibration curve, and the response in volts is going to go on our y-axis. Okay? In doing so, we can get the concentration for an unknown. Okay? It'll be log of concentration on x. And as I said, you can determine if the electrode response is Nernstian based on this direct calibration curve, because the slope is equal to beta times RT, natural log of 10, over n times f. You know all of the values here, and you know the value of the slope from your calibration curve, so you can calculate beta. Okay? If beta equals 1, the response is Nernstian, which is what we expect. Any large deviation from this means that the electrode is probably not responding correctly, and we probably need to get you a new electrode. You can also determine the K value from the intercept as well. Okay? Things are a little bit different for standard additions, and so let's look at that next. So if we look at the Nernst equation for our standard additions curve, it should look pretty similar to what we did for direct calibration. The main difference being what's inside the log. Let's define these terms. V sub 0 is going to be the volume of the unknown. This is what you start with. Okay, this is what you start with in your beaker. C sub x is the concentration of your unknown. V sub s is the volume of the spike. So the concentrated chloride solution that you're adding, that's the volume. And C sub s is going to be the concentration associated with that spike. Okay? And since we're multiplying volumes times concentrations, we're ending up with moles. So we have moles plus moles over volume. So that's moles per liter. And that's how this works out in the equation. So the other thing I want to do is say that beta times RT natural log of 10, that's all going to be called S in our equation. And then we're going to rearrange this equation and use the rules for logs to come up with an equation in the form of y equals mx plus b. So we'll have v sub 0 plus v sub s times 10 to the e over s is equal to 10 to the k over s times v sub 0 c sub x plus 10 to the k over s times c sub s v sub s. Okay, and this is in the form of y equals mx plus b. Okay, where our slope m is equal to 10 to the k over s times c sub s. And we're going to plot the volume of our spike on our x-axis, and v sub 0 plus v sub s times 10 to the e over s on our x-axis, or excuse me, our y-axis. And remember the E, the potential is in volts. We're going to end up with a plot that looks something like this. And the x-intercept, where it crosses on the negative side, is going to be equal to, if we rearrange this equation, the x-intercept is going to be equal to minus v sub 0 c sub s, excuse me, c sub x over c sub s. Okay, so it's v sub 0 times c sub x over c sub s. Again, the negative sign of the negative intercept. And if we know our volume of our unknown, we know our concentration of our spike, so we can solve for the concentration of unknown using this. Your handout goes to the derivation of this. Okay, so take a look at that. And please bring your laptop with you to lab if you have one. If you don't, feel free to use one of the lab computers. We want to make sure that you can work through all of this in lab. The actual measurements themselves don't take very long, so that we can spend a good amount of time on our calculations.